In this discussion video, we will do some examples where we are given functions and we want to figure out where they are increasing and decreasing, where they're concave up and down, and where they have local mins and local maxes, and any points of inflection. Okay, so I want to look at problem 2, parts B and C from worksheet 10. So we have this function g of x and this function h of x. And I want to give you 12 total minutes to try these two questions. All right, 4, 3, 2, 1. Pause it. Give yourself 12 total minutes to try these questions. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 12 total minutes. Let's talk about it now. So for g of x, let's start off with the increasing, decreasing part. So increasing, decreasing. All right, so I'll need to take a derivative and do a sign analysis, sign chart on the derivative. And I could do quotient rule right away, but it helps if I simplify this function first, because I can split this up as x cubed over x minus 2 over x, and that simplifies to x squared, and then minus the 2 over x, and for taking the derivative of that, it's helpful to rewrite this as minus 2x to the negative 1, because now when I do the derivative, it's easier. I don't need quotient rule. For the x squared, that derivative is 2x. For the next term, the minus 1 comes down, and I'll get a plus 2x to the negative 2. Now let's simplify this. So we get 2x plus 2 over x squared, and I can get a common denominator. So let's multiply the first term by x squared over x squared. So this gives us 2x to the third plus 2 over x squared. And now I can factor 2 out of the top to get 2 times x to the third plus 1, x to the third plus 1 over x squared. Okay, so that's my derivative. I need to now figure out when is this equal to 0 and when is it undefined. So g prime of x, this is going to be equal to 0 when, for the fraction to be 0, the numerator has to be 0. So this happens when x to the third will be equal to negative 1, and that happens when x equals negative 1. When is this undefined? So my derivative is undefined when the denominator is 0, and that occurs when x is 0. So these are my cut points of the derivative function. These are now going to go on a number line. Okay, so I'm going to make a number line. I'm going to put negative 1 on it and 0 on it. Any value that makes the derivative either equal 0 or that makes it undefined goes on the number line, even if it's not in the domain of the original function. So like 0, for example, is not in the domain of the original function. It still goes on the number line because it's still a place where the derivative is undefined. Okay, so now I got to make a sign chart. Let's put the factors of this function as rows. So I will put 2 times x to the third plus 1 all together, and then I'll put x squared underneath that. Okay, and then I'm going to keep track of g prime of x and then g of x. So I may need a little bit more room here. All right, so just scooching things up a little bit. So let's make our rows. So making our rows, and then let's make our columns. Okay, so for 2 times x to the third plus 1, I got to focus on the x to the third plus 1. And that's going to be positive when x is bigger than negative 1. And multiplying by 2 isn't going to affect the sign. So this is positive when x is bigger than negative 1. That's over here. It's going to be negative when x is smaller than negative 1. X squared is going to be positive everywhere because this is an even power. No matter if I plug in a positive number or a negative number, it's going to be positive. It's going to be positive everywhere. Okay. So now I need the sign of g prime of x. G prime of x takes these factors and it divides them. So if I have a negative number divided by a positive number, that's going to be negative. Positive divided by positive, that is positive. And positive divided by positive, that is positive. Okay, so when our derivative is negative, that means the original function is decreasing. It is going down. And when the derivative is positive, our original function is going up. Same thing here. It's going up. It's going to be increasing. So writing that down, we have that g is increasing. There were 2 intervals where it was increasing. On the interval from negative 1 to 0, union 0 to infinity, we might notice that if I go back to the number line, these are sort of consecutive intervals. They're sort of back to back. So in lecture, we saw an example of consecutive intervals, and we were able to just say, oh, it's just continuous the whole way. Sorry, increasing the whole way from -1 onwards. I can't do that here because my original function is not continuous at 0. I can't plug 0 into this function. So I can't combine two consecutive intervals like that, even though they're both increasing, when this cut point is a place where it's not continuous. So if I write that down, we can't combine these since our function g is not continuous at x equals 0. If it had been, I would have been able to combine those into 1. Okay, and g is decreasing on just one interval from -infinity to -1. Okay, so I'm going to box these. This is where it's increasing and where it's decreasing. Graphically, what's going on at 0 is it turns out my function has a vertical asymptote. So there's a vertical asymptote at 0, and then it's increasing from -1 to 0. So I have a thing like, oh, it's increasing up to that vertical asymptote, and then on the other side of the vertical asymptote, it's increasing again. So I might be doing something like this. But I can't just say, oh, it's increasing the whole way from -1 to infinity, because this function isn't even defined at 0. So that wouldn't be correct. All right, so let's erase this. All right, so now let's find local mins, local maxes. So going back to the question, it said, use the results to locate the x values of any relative just means local extreme points. Okay, so I'm going to go back to my number line for this. And at -1, my function changes from decreasing to increasing. So that gives me a local min there. There's going to be a local min at x equals -1. The other thing that I need to be able to say that, oh, it is a local min, is my function needs to be continuous there, the original one. And there's no problem with plugging -1 into this, so our function will be continuous there. So the graph will look like this. It will have a local min. So writing that down, there is a local min at x equals -1. And I'll write the reason why. It's since our derivative g prime changes from negative to positive. So the original function g changes from decreasing to increasing. And because our function is continuous there and it changes from decreasing to increasing, that gives us that local min. Okay, so we've done the increasing, decreasing, max, min part. We are ready to talk about concavity. So for the concavity now. All right, so for this, we will need the second derivative. Remember, our first derivative was 2x plus 2x to the -2. If I do the derivative of that, the derivative of 2x is 2. For the next term, the -2 will come down and give me -4. And then I'll get x to the -3. So let's simplify this. This is 2 minus 4 over x to the third. And if I get a common denominator, we get 2x to the third minus 4 over x to the third. Okay, and now I could factor a 2 out of the top to get 2 times x to the third minus 2 over x to the third. Okay, so we have our second derivative simplified. We're now ready to start to make a sign chart of this, but I need to first figure out when is that second derivative going to be equal to 0 and when is it undefined. So this is going to be equal to 0 when the numerator equals 0, which will happen when x cubed is 2. And if I cube root both sides, we get x equals the cube root of 2. Okay, and when is it undefined? Well, the second derivative is undefined. When the denominator is 0, and that happens when x is 0. Okay, so I take these and I'm going to put them on a number line. So I make a number line, and I'm going to put tick marks at these values. So I put one at 0, I put one at the cube root of 2, and then I write each of the factors of my second derivative as a row. So I'll put 2 times x cubed minus 2 all together. I'll put x cubed underneath that. And then I need to keep track of the second derivative and the original function. What it will mean about the original function. Okay, so let's split this up into rows and into columns. Okay, and now let's check the signs of each of these factors. So if I focus on the x to the third minus 2 part, that's going to be positive when x is bigger than this cube root of 2. It's going to be positive over here. The 2 in front won't affect that sign. If I had multiplied by a negative number, like negative 2, it would have flipped all the signs. Okay, and then when x is less than the cube root of 2, it'll be negative. So we get negatives over here. And then x to the third is positive when x is bigger than 0. So over here, and it's going to be negative when x is less than 0. So negative over here. Okay, so now for my second derivative, my overall thing, I'm sort of dividing these two. So a negative divided by negative, that's going to be a positive. Positive divided by positive is positive, and negative divided by positive, that is negative. Alrighty, so in terms of the original function, when our second derivative is negative, the original function is concave down. And when the second derivative is positive, the original function is concave up. So concave up in both of those regions. Okay, so we're ready to write down these intervals. So we would say g is concave up. It is concave up on the interval from negative infinity to 0, union the interval from the cube root of 2 on to infinity. Remember, our convention is when we write these intervals of concavity and increasing and decreasing, that we'll always use open intervals. That's going to be the convention we use in our class. And then g is concave down. G is concave down on that middle interval, 0 to the cube root of 2. Okay, and the question also asked for inflection points. So inflection points, it wanted the x values of any inflection points. Okay, so at an inflection point, the concavity has to change. So that happens at cube root of 2. It definitely changes there from down to up. It also changes at 0 from up to down, but there's a problem with 0. The problem with 0 is for something to be an inflection point, the original function needs to be continuous there. And this original function, I can't even plug 0 into it. 0 is not even in the domain. So it's definitely not going to be continuous there. So because of that, the only inflection point is where x equals the cube root of 2. Okay, so I'm going to box this, and I'll write down why. Again, there's no inflection point at 0. So g, our original function, is not continuous at x equals 0. So that means x equals 0 is not an inflection point. I gotta be careful about that. All right, so that is part A of this example. Well, let's move on to part B. All right, just moving that down to give myself some more room. Okay, all right, so here's part B. We have this function h of x. So all of the same stuff. Because this function is so similar, I'm going to skip some of the steps. And I'm just going to say that it turns out, I'm just going to tell you what the derivative is after we simplify it. The derivative, after it's simplified, ends up being x to the third plus 4 over x to the third. So I'm skipping some steps there. Okay. And now I need to figure out, when is this equal to 0? When is it undefined? Well, this equals 0 when the numerator equals 0. And if I set this equal to 0, I'll get like x to the third equals negative 4. And if I cube root, we get x equals the cube root of negative 4. So that's when the whole fraction equals 0. And this whole fraction is undefined when the bottom is 0. And that happens when x is 0. All right, so we are ready for a sign chart of the first derivative. So I'll make a number line, and I put those points on it. We have the cube root of negative 4. That's going to be a negative number. And then 0. And then I write all the factors that showed up in my derivative. So on the top, we had x to the third plus 4. Let me write that 3 better. So this is x cubed plus 4. On the bottom, we had x cubed. Then I'm going to keep track of the derivative. Let's see, it was h prime of x, and then h of x. Okay. And now making columns. Okay, so for x to the third plus 4, that's going to be positive when x is bigger than this cube root of negative 4. going to be positive on these sides. And if I plug in something smaller than the cube root of negative 4, it's going to be negative. And x to the third, we've already seen in this video. This is positive to the right of 0 and negative to the left of 0. Okay, so when I put those together, the two negatives are going to make a positive, because a negative divided by negative is positive. Two positives will make a positive. Positive divided by positive is positive, but a positive divided by negative is negative. Okay, so if the derivative is positive, that means the original function is increasing. Here as well, it's going to be increasing. When the derivative is negative, the original function is decreasing. So let's write down those intervals. H is increasing on the interval from negative infinity to the cube root of negative 4 union the interval from 0 to infinity. H is decreasing. It is decreasing on the middle interval from the cube root of negative 4 to 0. Okay, and let's also classify local maxes and local mins. So at cube root of negative 4, my function changes from increasing to decreasing. So we'll have a local max. And our function is going to be continuous at the cube root of negative 4. So that's good. I need that. So there is a local max at the cube root of negative 4. For this problem, I'm going to skip the justification. I'm instead just going to point to it and say, you should justify why. If this was a homework question, quiz question, exam question, you should justify why there's a local max there, like we did in the previous example. Okay, and at 0, my function changes from decreasing to increasing. So it certainly looks like there's going to be a local min. There's actually not. There is no local min at 0, since. Give the video a quick pause and see if you can figure out why. I'm not going to count it down, but I'm going to trust that you paused it to think about it. There's no local min at 0 since our function h is not continuous at 0. So to apply that first derivative test, which lets us check whether our values are local mins or local maxes, those numbers need to be values at which our function is continuous. But 0, I can't even plug into the original function because it would make the denominator 0. Okay, so it's not going to be a local min. Graphically, the type of thing that might be happening there is we might have a vertical asymptote at 0. So even though the function is sort of decreasing to the left of it and then increasing to the right, that doesn't necessarily mean there's a local min because our function wasn't even continuous here. All right, so I'm going to box this. This is the increasing, decreasing, local maxes, local mins part of the problem. So we are on to the concavity part. For that, we'll need the second derivative. And again, I'm just going to tell you what it becomes after we evaluate it. It turns out that our second derivative will be equal to negative 12 over x to the 4. So we need to figure out when is this equal to 0? And for a fraction to be equal to 0, the numerator would have to be 0. But this numerator is negative 12. That's definitely never going to be 0. So this never equals 0. And then I got to figure out when is it undefined. It's undefined when the bottom is 0. And that happens when x is 0. So we're ready for the number line. So let's get our number line going. And I put, the only value here was x equals 0. I put that on the number line. And then I would say this function is simple enough to where let's just write the whole thing. Let's just write h double prime of x, which is negative 12 over x to the 4. And then I'll keep track of h of x underneath that. But if I wanted to write a row for each factor, like maybe I have a row for the negative 12 by itself, and then a row for x to the 4th, and then combine them to make this, I definitely could. Okay. But with this function, I noticed that x to the 4th will never be negative because of the even power. And then the negative 12 will make that result be negative. So it's going to be negative on both sides. And when the second derivative is negative, the original function is concave down. So it's concave down on both sides. We're ready to write down our intervals. Okay, so giving myself more room there, we could say h is concave down on the interval from negative infinity to 0. and 0 to infinity, I can't combine these even though they're consecutive intervals and the same thing is happening on both, because my original function is not continuous at 0. I couldn't plug 0 into the original function. So we can't combine, since the original function h is not continuous at 0. Okay, so where's this concave up? Well, never. H was never concave up. And for inflection points, well, there are none. There are no inflection points, because there weren't even any points where the concavity switched. Okay, so this is our answer for concave down and up and inflection points.